Welcome back to class. This is chemistry class. I'm Mr. Joseph and I'll be your chemistry instructor. This is the concluding part of the electron configuration and chemical periodicity. We have done module 1, 2, and this is the concluding part of this section. Now, in electron configuration and chemical periodicity, we have looked at the definition of electronic configuration. We have looked at the stratification and the structure of the periodic table. We have looked at the guideline in writing electronic configuration or electron configuration. We are now exploring certain important laws and principles that guides or that actually check for the configuration of electron in relation to the chemical properties. Now, we quickly explore in this particular aspect. We want to look at the last part, and in this particular teaching, at the end of the lesson, you will be able to explain the Hunds Rule. You'll be able to enumerate the factors that associate with the Hunds Rule. You are going to be able to discuss Aufbau's principle. You're going to be able to apply the Aufbau's principle in electronic configuration, and finally you'll be able to discuss the connection between the Aufbau's principle and the Hunds Rule. This is what you tend to learn as you follow to the end of this video. Now, looking at the orbital occupancy for the first 10 elements in the periodic table, from the hydrogen to the neon, looking at the electronic configuration and looking at the placement of electron in their orbital. Now, take a look at this. We have their orbital, actually the inner orbital, then followed by other subsequent orbitals. If you look at the atomic structure, this is exactly the way an atom looks like. Now, if you look at this, atoms of hydrogen, which is having atomic number 1, has 1 electron in its outermost shell. So it means that we are going to have 1 s. Now, going to the helium is having 1 s2 because it has 2 electrons in its valence shell. So looking at the second period, that is the first period. In the first period, you have hydrogen and helium, and each of them actually occupy 1 s block part of the periodic table. You know, the periodic table has been stratified. So the 1s and 1s2, which is for hydrogen and helium, actually is in first period of the periodic table. Now, coming to the second period, you understand that apart from the first shell, now the second period, now they have added another shell. So it means that as a new shell is added, the energy level is affected, and then it means that there's a shift from the s orbital to the p orbital. So all through the second period, you are going to see both s and p. In first period, you're going to see only s orbital. So in second period, you see s and p orbital. In third period, you see s and p, but you now see both 2p and 3p orbital. So looking at this, the trend, the second period, now lithium has 1s2, 2s1. So if you want to write the electronic configuration, start from the beginning. Start from the lowest energy level. Start from the orbital that has the lowest energy, which is s. And as you progress from s to p, the energy tends to increase, the number of shell tends to increase, the number of orbital also must increase. So you go from 1s1 hydrogen, 1s2 helium, 1s2, 2s1 lithium. Then when you are going to boron, it means that you're going to have 1s2, then 2s2. If going to, that's for beryllium. Now for boron, you're going to have 1s2, 2s2, and then 2p1. You can see that there's a transition from the p orbital now to the p, from the s orbital now to the p orbital. Now, if you follow that sequence, for carbon, 1s2, 2s2, 2p2. For nitrogen, 1s2, 2s2, if you add 2 plus 2, you have 4. Minus it from the total number of the atomic number for nitrogen, which is 7. So 7 minus 4 will give 3. So you shift that 3 electron to the p orbital. That's how to write electronic configuration. Now it's now simplified. It's now well explained. It's now well stratified in such that taking a glimpse of it, you'll be able to have a better understanding. So start from the beginning, use the principle, use the guiding principle, apply them, and then you get your desired result. Now, going further, look at the partial orbital diagram and electron configuration for the element in period 3. Now, please take notes. This is where you need to take a very serious cognizance and pay a very rapt attention in the course of this video, because this part actually confer the central message of this teaching. So the atomic number of element, which is very important, I've told you this, you need to know the atomic number even without you being given. In some cases you will not be given the atomic number, but you just have to know them. You just at least the first 30 to 40 elements in the periodic table, which I've taken you through the first 30. So you need to understand how it works, the arrangement, the position, the atomic number, the atomic mass possibly, and you need to also know how they are arranged in the periodic table. So for sodium, sodium has atomic number 11. So it means if you have graduated from 1s2, 2s2, 2p6, 3s1, that means you have in 1s orbital you have 2 electrons, one going up, one coming down. In 2s orbital you have 2 electrons, one going up, one coming down. In 2p orbital you have 6 electrons, you have one in the first partition, one going up. Look at how p is partitioned. P orbital is divided into 3 because in each of the box it must have maximum number of 2 electrons. That's why we have to divide the orbital into degenerate orbital. Degenerate orbital means suborbital inside orbital, like one orbital being split into different suborbital. That's why we call them degenerate orbital. So you may see this in your exam, you may come across this in textbooks, you may see this online. So degenerate orbital of 3p is stratified into 3, and the idea, the goal is that each of these boxes can actually accommodate maximum number of 6 electrons. So from the 3s you have 1 up, then 3p. Now supposing that the electron will come into this 3p, one will go up, one will go up, one will go up. You feed them singly first before you fill them, you pair them. So that's what the Hund's principle is telling us. So it must be singly filled before you now pair them. That is very important. So the from magnesium, now you see this 3x has turned to 2. Now for aluminum, this 3x is having 2, then it has transited from the s orbital now into p orbital. So aluminum electron has entered into the 3p degenerate orbital. So you have 10. Now if you want to write it in condensed form, I told you that you can write in a condensed form. Neon has maximum number of what? 10. That's the atomic number for neon. So you put neon in bracket. 10. Now sodium is 11. It means 11 minus 10, that's 1, 3s1. 11 minus 12 minus 10, 2, 3s2. 13 minus 10, 3, 3s2, 3p1. So that's how you follow. That's the sequential order. You must follow this order for you to be able to do the right thing, applying the correct principle and getting the best result you can ever get. So look at it. When you get to 14, 15, 16, 17, and 18. Now look at it. Now we have a perfect arrangement in argon. Look at it. 1s2, 3p6. That means it's a perfect arrangement. So we can now use argon again to form another subsequent condensed form and pattern of the electron configuration. So instead of now going to potassium, now writing 1s2, 2s2, 2p6, 3s2, 3p6, then 4s1. You don't need to stress yourself. There is a condensed formula, condensed principle. You can condense it. You can, what they call shorthand. You can use the principle. It's applicable. It's allowed in chemistry. So you look for a particular element that is having its orbital completely filled with electron, and this is it, argon here. So you look at the sequence. Look at 1, look at 2, 1 2 3, 1 2 3 4, 1 2 3 4 5, 1 2 3 4 5 6. That's the strength. Like that, you continue like that, but follow the sequence from S, 1s to 2s to 2p to 3s. Now after 3s you have 4s, then you have 3p, 3s, 3p, 4s, and 3d. That is the sequence. You must follow the sequence if you must actually get it. Now see this, please take a look at this. I try to condense the first 18 elements in the periodic table because all of them are from period 1, 2, 3. So these 3 periods, let's collate them, let's make them a quorum, let's chemicalize them, let's synthesize them further using the electron configuration in the first 3 periods of the periodic table. Now look at it. Hydrogen hanging at the first, helium at the second in the same period, then lithium to neon in the second period, sodium to argon in the third period. Now look at it. The replica, I replicated what was done in the previous slide into this, but in another format, so that whichever way you see it in exam, you can be able to get the correct answer and by applying the correct principle and doing it the right way. So hydrogen 1s2, do you see? So helium hydrogen 1s1 rather, then helium 1s2, lithium 2s1. Then you keep increasing the number of electrons on the x, keep increasing. When it reaches 2, go to the next orbital, which is p. Then 1s1, 1s2, 2s1, 2s2, then 2p1. That's how to follow the sequence. So you go from your right to your left, from your right to your left. You follow that sequence and you're going to get the best answer. Now, similar outer electron configuration correlates with the similar chemical behavior. Please note this. In fact, you're going to see questions coming up from this electron configuration. The similar outer electron configuration has a correlation, a sequential correlation with their chemical behavior. In other words, the chemical behavior forms the basis of the resolution that happen, the similarity that actually occur within the outer electron when you are writing your electron configuration. Now look at this. Look at this table. Partial orbital diagram and electron configuration for the element in period 4. Now we have looked at period 1, period 2, period 3. Now let's look at period 4. Please look at this. We are coming gradually to the end of this teaching, but you must watch this video to the end because this is the fundamental part. This is the part you cannot afford to miss. Now look at the period 4. We are tracing from potassium to nickel, from potassium. Now I told you of some exceptional rules. There are some exceptions that you must follow. This exception actually from chromium and copper, how filled and filled sublevel are unexpectedly stable. You must understand this rule that half filled and filled sublevels are unexpectedly stable. So how does this work? Let me show you how it works. Now, atomic number 19 is for potassium, 20 is for calcium, 21 for scandium, 22 for titanium, 23 for vanadium, 24 for chromium, 25 for manganese, 26 for iron, 27 for cobalt, 28 for nickel. And if you go further, you will see that we have 29 for copper and 30 for zinc. But we are not, let's just limit the circumference of our explode within 19 to 28 electron elements in the periodic table. Now look at 19. Now I told you argon has 18 completely filled. Now just write the argon. A 19 minus 18 is 1. Just put your 4x1. If you go to 20, which is calcium, so you keep filling from the 4s Now we said period 4, 4s. Now look at it. Let me take you through again. Period 1, 1s. Period 2, 1s, 2s. Period 3, 1s, 2s, 2p, 3s. Period 4, 4s. Are you following the sequence? This is how it works. Anything outside this is not chemically acceptable. It's not acceptable in chemistry. You must follow the sequence. Now, if you go to scandium, scandium is the very first transition element in the first row of the periodic table of the transition, the D block element. Now, remember, we said the transition element are D block element. So it means that this scandium, it will go beyond the 4 orbital. It will enter into D orbital. That's why you are seeing 4s2, 3d1. That's how it works. Then for titanium, you have 4s2, 3d2. For vanadium, 4s2, 3d3. For chromium, now look at it now. This is the exception. You must understand this. For chromium now, you have, instead of you having 4s2, 3d6 or 3d4, it will not be stable because it can either be completely filled or half filled. So you now fill the 4s halfway, you fill the 3d orbital halfway. So you put it like they say, half bread is better than none. So instead of somebody, a wife and a husband in the house, somebody has eaten, somebody has not eaten. Maybe you have 4 slices of bread. So instead of the husband taking the 4 slices or the wife taking the 4 slices, why can't you share 2? So everybody will be stable and things will be balanced. And you move on. So that's how it works here. It's applicable. So instead of giving 4s2, then 3d4, pair it now, share it now, 4s1, 3d5. Then you go to manganese, 4s2, 3d6. You go to iron, 4s2, 3d6. You go to cobalt, 4s2, 3d7. You go to nickel, 4s2, 3d8, 3d9, and 3d10. So 3d10 is for zinc, and that is why I told you earlier that zinc actually does not exhibit variable oxidation state because it has its degenerate orbital completely filled with electron. So looking at it right here, you will see other elements, other transition elements lining up and their various electronic configuration. You see that D, if you look at 29, which is copper, has its D block orbital completely filled with electron, but its X orbital actually lack 1, while that of zinc is completely filled. This is the chemistry I'm trying to explain. Now, going ahead, looking at this particular periodic table. Now, where we started from, I started by stratifying the periodic table and giving it the structure. This is the amplified advanced structure I gave earlier, and this now shows the trend and the electron in each of the period and in each of the group based on the orbital. You know, the S block, the P block, and the D block. And F. Look at the first set. The first set here is the S block orbitals. So from here, looking at from hydrogen to this particular second row is actually meant for S block. Now going to from boron here, from helium here towards down, you see this is the P block orbital, then the middle one is the D block, the last one is the F block. Now look at the relationship between the orbital filling and the periodic table. Can you now look at we want to look at the sequential relationship. Now look at it. The first one is the first energy level, which is what? 1s, followed by 2s. So 1s, then 2s with 2p actually have the same resolution. 3s, 3p, 4s, 3d, 4p. This shows the synergy, the hybridization between the sub-energy level. This shows that in each of these energy levels, there's a resolution within and between them so that they can be able to strike a balance even among themselves. So this shows the trend. Now, looking at this, common tool used to predict the filling order of sublevel. Now, please, this is the core part of this teaching. Look at it again. Look at it. I've seen some students making mistake trying to throw this up instead of bringing it down. It must actually come up from the 1s. Do you see it? The first one, 1s. After 1s, 2s. So when you are done with 2s, go back up here. Don't start from 3s. You go to 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 3d, 6p, 7s, 5f, 6d, 7p. This is the trend. Please, on no account, under no situation or circumstance should you start from 3s when you are done with 2s. You go from 2s to 2p to 3s. Under no account should you start from 4s after you are done with 2p. You go to 3p before you come to 4s. That is how it works. If you flout this rule, you cannot actually get it right. So to get it right, follow the rule. So the end value are constantly horizontal. Why? I told you end value is the size. Why end value is the shape, which are constantly vertical. Now if you combine the values, you see m plus l, which are constantly which are very constant when you look at it from the diagonal point of view. Diagonally speaking, they are very constant, both the shape and the size, the end value and the L value. Now look at this. Let me show you this now. Now look at the similar reactivities within the group. Now if you group elements together, there are certain reaction that takes place within that group. Orbitals are filled in order of increasing energy, which leads to outer electron configuration that recur period. Do you see the periodical reiteration, reoccurring of this energy level, one leading to another, which leads to chemical properties that reoccur periodically. So you see that there's a particular trend that each of them is following or follows as we go from one element to the other. Now, categories of electron. There are 3 basic categories of electron which you must know. In fact, if you check most of these common, I don't want to mention textbooks, but most of these most profound, well-known textbooks, most of them are not having this information. So it's very important you pay attention. This information is very vital. There are 3 categories of electrons. A chemist will tell you this, and if you're a bona fide chemistry student, you must be able to know this. Number 1, we call them core electron. Core, C-O-R-E, core electrons. These core electrons, they fill all the lower energy level of an atom. All the lower energy level of an atom. We call them core electron. Number 2 is the outer electron. Those ones that you see with the highest energy level. They are on an atom. Those electrons in the highest energy level, they have the end value. They are on the atom. We call them outer electron. They are not actually involved in chemical combination. They are not involved in chemical bonding. They are not involved in any further chemistry analysis. It's only valence electron, which is the third part. So the first one is the inner electron, core electron. The other one is the outer electron, which is the second layer of the core electron. And then the last one is what we call valence electron. That is, electron at the outermost shell. So these are what is important fundamentally for further chemical analysis. So these are what you see when we talk about chemical combination: hydrogen combining with oxygen, oxygen combining with carbon. And when you look at carbons of chemistry, talk about organic chemistry. There can never be reaction within 2 atoms or 2 elements except that the valence electron is utilized, which forms the base. So let's look at general observation as we bring it to a close. General observation about periodic table. Have you observed the 3 things? These 3 things. Number 1, did you observe that the group number equals the number of outer electron? That is, the outer electron, those with the highest value of n, the main group element only, they form the number of the outer electron, and this is the basis upon which the elements are arranged in the periodic table. 2. You also observe that the period number is the end value of the highest energy level. So period 1 energy level, period 2 second energy level, period 3. So that is how it works. These are things that you must understand about periodic table. It's very important. Then you also observe that the end value square, that is n square, n raised to power 2. Do you observe that it gives the total number of orbitals in that energy level? Have you observed this? You need to observe it. Go back and check the s, the p, the d, and the f orbital. You will see that n raised to power 2 actually will give the maximum number of electrons in the energy level. So for instance, s, n raised to power 1, that is 2n raised to power 1. 2 times 2 raised to power 1 is what? Is 1. Now, for the second one, 2n raised to power 2. If you look at it sequentially, you will see that 2n squared gives the maximum number of electrons in the energy level. Let's quickly solve this problem as we bring it to a close. Using the periodic table, give the full and condensed electron configuration and partial diagram showing valence electron and number of inner electrons for the following element. Do not worry, don't give yourself headache. It's very straight, very direct, and very simple, following the principles I gave you and following the guidelines. Then if you use the atomic number for the number of electrons in the periodic table for the order of filling of the electron orbital, then you are going to now get the condensed configuration, which consists of the preceding noble gases. The first noble gas in the periodic table, what is it? The first noble gas, very first one, is helium. The second one is what? Is neon. The third one is argon. So if you follow sequentially, you will just use that condensed formula. As you write argon, just count the number of, like 9Z. They say Z is 19. That means it's potassium. Then if you put the condensed one, 18, which is argon, just add your 1 to the 4s orbital. 4s orbital because it's already in period 4. 3s orbital because it's in period 3. 2s because it's in period 2. That's how it works. It's very, very simple. Then following the principle, polar exclusive principle, Aufbau's principle, and Hund's principle. These are 3 fundamental principles that we must follow. You see that the first electron will actually go up. Now look at it. For 42, write your condensed crypting, then follow the order. Put 5x1, 4d5. If you add it together, you are going to get the exact number 42, and that will give the exact number for the electron configuration. The same thing with lead, which has atomic number 82. The same thing is applicable. So finally, what is the key principle? Please hear this and hear it well. All physical and chemical properties of the element are based on the electronic configuration of their atom. Can I say this again? All physical and chemical properties of the elements, they are all based on the electronic configuration of their atom. So in other words, the electronic configuration of the atom actually is a resultant factor of the physical and the chemical properties of any element in the world that you are considering. So here we end the electron configuration and periodicity. I would like you to subscribe to our YouTube channel, watch more of our videos, be on the lookout for updates, because in the world of chemistry there's updates every now and then. So you need to keep yourself abreast and keep yourself updated on the new trend, the new waves, the new set of questions, the new set of topics wherewith examiners are bringing out questions. So when you follow us up and you watch our video, you're going to see more of our videos that will give you the updated trend in the world of chemistry. I remain your chemistry educator. Till we see you again, take care, and I will see you again. Bye.